Welcome to our weekly live session. Like I was just telling the people who attend live, this is going to be probably one of the last live sessions where we have that many slides. Okay, we are getting into our routine, meaning that every Monday at 7 p.m. we're going to have our live session. And the purpose of the live session, it's located at the end of the module. Okay, right before the deadline, Monday 11:55 p.m., where we switch to the new module. So really, the purpose of the live session is to be an opportunity for all of us to get together and to wrap up the module. So that means generally students coming with problems that they have encountered on practice exercise, so I can help them work through a practice exercise, or students coming with questions that were not fully addressed in the forum during the week, things of that nature. So it's really meant to be interactive. However, as you know, we just went through our Getting Started week, so there are probably not that many questions yet, that many problems, because most of the time the Getting Started week is about installing software and going over administrative stuff, the syllabus, etc. So not really nothing there that warrants, you know, a Q&A session. However, if you have questions, I'm talking to the people attending live. If you have questions, feel free to ask them anytime. Feel free to ask them after the session if you don't want them to be recorded. And for those of you watching this afterward because you could not attend, same thing. So feel free to use the support forum, etc. So I'm not saying that the question shop is closed officially on the syllabus, etc. Far from it. But since we won't have probably many of those Q&A, I'm going to use, again, for the second time, I'm going to use this session to go over a bunch of slides. And this time what we're going to do is directly related to programming. So last week the slides were really general advice about how to work in this offering, how to work on an online course, things that were that were useful for students in the previous semester, things that were less useful. So now that we have done all of this, this slideshow is going to be really about programming. And it's actually a good slideshow to put as the first slideshow on programming, simply because it's about the process of programming. So the programming thought process. How does a programmer think his or her way through a problem? So it's going to be relatively general. I'm going to make an effort to illustrate every of the ideas with Raptor, which is the first of the language we are going to start studying with the module released tonight, module 101. Okay, so I'm going to anticipate a little bit on module 101, just show a few little things with Raptor, but it's going to be really easy. And we are going to focus on the big picture here. We are going to focus on really what does it mean to program. Okay, what are the skills that you need to develop? What is the role of each of the skills in the grand picture of programming? And pretty much I'm going to do my best to give you almost, and the keyword here is almost, an algorithm on how to program, like a step-by-step process that you can follow, and that's going to help you find your way out of a programming problem. So the keyword is almost, because if I had such an algorithm, then that means I would be able to automate the activity of programming. As we're going to see, this is not yet quite true. Okay, we cannot really automate programming yet. So we need humans to do programming. So, all right. So overview for this presentation. I'm going to try to very briefly motivate why we are devoting this session, you know, to discuss about how to program explicitly. Then we are going to dissect what some people refer to as the one programming skill into a series of skills, about 5, 6 of them. Okay, so we are going to pretty much make it obvious, make it evident that programming is just not a single skill that you learn as one entity. Okay, it's actually made of different skills that have to come together in an organized manner. So then we're going to try to, after we go through every skill and we explain, you know, the role they play in the overall programming process, we are going to try to present a diagram that summarizes the programming thought process in one diagram. Okay, and this is going to be pretty much your guideline as you are working your way through this semester, and as you are working your way through IT program design after this class. You are going to have to keep in mind this diagram and keep applying this method to get yourself out of programming problems, to be able to go from a set of requirements to a finalized program that works and implements accurately the requirements. Okay, and then we're going to, as we explains the different programming skill, as we present the different programming skill in the step, we are going to actually repetitively show how to apply this. So I'm going to show a skill, I'm going to show how to apply it with Raptor, as a flowchart interpreter that we are going to use for the first 3 modules. And so I'm going to try to make it very pragmatic, very illustrative, okay, with a lot of examples. As usual, anytime questions are welcome, please feel free to interrupt, okay? So you can do so by typing your question in the chat window. You can use the hand raise icon like I'm doing right now. Okay, there are all sorts of ways that you can notify me, take the microphone and say I have a question. There are all sorts of ways you can notify me that you have a question. Please do not hesitate to do so. Okay. All right, let's get started. So let's jump in. And we are going to start with the motivation. Why teaching a programming thought process? So sometime I'm going to refer to programming thought process as PTP, just to keep it short. Okay. So the idea here is that there are different ways that you can learn things in general, okay? And generally learning by imitating somebody leads to reinventing the wheel. If we are trying to teach you to program, the idea here is to make the programming process itself explicit. Why? So that you can observe it, so that you can understand it, so that you can replicate it, okay? So there are different ways to teach programming. None of them is perfect. Obviously, it depends on the combination of teacher and learner, you know, what works best for both of them. But here what we're really trying to do is we are trying to make everything explicit. We are trying to be as explicit as possible in what you have to do when you program, as opposed to let you figure out it for yourself just by looking at examples of good programmers doing their job, okay? So that means for programming specifically, we already talked about that a little bit last week, okay? The different ways that we have to try to give you the programming skills are to show problem solutions, okay? Pairs of problem solutions, sort of like what the textbook does, okay? And we talked about that one last week. This is actually a passive exposure to give you an idea of what a good program looks like, but it doesn't really focus on the programming process itself. How do you write the program? How do you come up with those ideas? Then the second approach is to show you how it's done. And this is the job of the apprenticeship exercise. Then the third approach is to analyze the process of programming, to explicitly have a lecture or more lectures that are analyzing exactly what programmers do when they work. Okay, making it explicit. Guess what? None of these is actually right in and by itself. You will find people that can learn programming just by reading the textbook, and it comes naturally. Other problem, they just look at a skilled colleague work, and then they're going to infer automatically what they have to do. Other people need to have the process explicited to them. And then most people could benefit from a little bit of those 3 approaches. So this is why we really don't have like one approach that we're going to use in this course. We are going to use the 3 of them, knowing that most of the time this has been traditionally the only way to teach programming. If you go back like 5-10 years ago, this has started to find its way in many courses at different institutions in the US. You will see that referred to sometime as live coding. Okay, this is the same idea. Live coding, apprenticeship, cognitive apprenticeship, all of this is about showing you how to program. And then this one is less popular, I would say. This is not something that you will find in every programming course. There are a few of them, a few textbooks that are starting to employ this method. Our textbook is pretty much here. It's not using apprenticeship really. It's not using an explicit analysis of the programming process. So that's why we are supplementing it with those things in the course. So let's take a look at those programming skills. The first programming skill, there's going to be about 5 or 6 of them, as I mentioned. The first programming skill is tracing, also known as code tracing, also known as code reading. You'll find those terms. All of this is about understanding. And you can tell by my handwriting why I'm using slides, right? My handwriting is awful, so I apologize, but hopefully as I'm reading what I'm writing at the same time, you'll be able to understand it. This is scribble here is understanding. All right, so all of those terms are equivalent. And the idea of code tracing is very easy. You are given a valid meaning here two things. It means one, there are no bugs, and I'm going to try to make an effort to write legibly. And two, it implements all requirements. I'm going to abbreviate requirements like so, correctly. Okay, so correctly and all. So that means that your program is perfect, pretty much. So I'm going to give you a program that is already doing a job, and that is doing it correctly and completely, okay, without any bugs. Now, the goal of tracing is for you to develop the skill of being able to follow the execution of your program step by step, okay? So you're given a program. Without executing the program on the computer, just using your brain and maybe a piece of paper to keep track of what's happening, or an Excel document or a Word document to keep notes, okay? With just your brain, your understanding of what the construct of the language are doing, and this piece of paper to help you keep track of things, I want you to predict the output, the behavior of the program, okay? That shows that you understand the programming construct of the programming language we are using, okay? So that entails several things. That entails keeping track of the value of each variable that the program is manipulating. We are going to talk about variables in Module 101. Those of you who already got a head start and watched the lecture for Module 101, you know already what I'm talking about, but that's okay, that you don't need to have done that already to be ready for the session tonight. That means also keeping track of what is read from the user and displayed on the screen. So a program can obviously prompt the user to enter data with the keyboard. So you would enter, for example, an integer value on the keyboard, 42, enter. The program reads that value, stores it into a variable, uses it to do some computation, and eventually displays something on the screen. That can be a numerical result, that can be a text message, that can be even like windows and graphics and stuff like that, okay? But pretty much when you're tracing, these are the main things that you're keeping track of. The input-output, what is read from the program, from the user by the program, sorry, what is displayed by the program, and what is the content of every variable that exists in the program at every step of the execution. That allows you to go very slowly through a program and analyze exactly what it's doing. You will hear a lot, like if you have been working with Python before to come to this class, you are going to hear people talk about memory models, actually. The idea of a memory model is the programmer has in his or her head a model of what happens in memory for every instruction of the language, okay? And this is really essential, because this is what we try to do here by tracking the value of each variable. We try to have a map of what happened in the memory of the computer, in the memory of our program, as the instruction execute. So you can see how being able to do that, being able to read code and pretty much, I would say, think like a machine, right? And be able to do step by step what is happening here, you can see how that's going to be fundamental. That helps you understand how the program executes. Okay, so it's almost like having a scientific theory. What is a scientific theory? It's actually a model of something that allows you to do two things: explain a phenomenon and predict a phenomenon. So if you cannot explain and predict, chances are that you do not have a scientific theory of something. Okay, there's a little bit more to it, and trying to take a shortcut here. There's more about refutability of scientific theory and stuff like that, but we're not going to do a lecture on epistemology here. What I want to focus on is the idea that when you are reading a program, you need to have a theory of how this programming language operates in your mind, a model of how it operates. That means that each statement, you have to be able to translate it into actions in terms of reading data from the user, displaying data on the screen, and affecting the state, the content of all the variables in memory. Okay? So you have to be able to run the program in your head. If you cannot do that, you cannot do anything in programming. This is a first skill. View it as the bottom, the foundation of a pyramid of skills. Okay, this is the first skill. This is the easiest one to learn, actually. That's the good news. But the bad news is that if you somehow do not learn it because you don't put enough time, or you are not strict enough about really remembering what everything means, etc., then it's going to cascade very, very fast. There's going to be a snowball effect because you are not able to read code and predict its output. You don't understand really what code does. So when you write code, what you think your code is going to do is probably not going to be what the program is going to actually do when it executes. And then when you try to debug code, find errors in the code because you have a bad representation of what each instruction does, then you're going to replace bugs by over bugs, problems by over problems. There's no way around it. You have to absolutely master that tracing skill, no matter what you want to do in programming. Even if you just want to be able to program occasionally, or even just read a program. Okay, that's really, really fundamental. So let's try to illustrate that. The problem, obviously, is that this is our second live session. It kind of wrap up our first week. It's right before the deadline where our first getting started week will end. So we haven't yet learned any programming language. We haven't learned anything about programming, really. We were busy doing software installation and syllabus forensics. So instead, what I'm going to try to do here is I'm going to try to give you a taste of what the tracing skill entails. Okay, but every module that we're going to go through, I will use those live sessions to supplement, the other material with example as needed, if you have questions, etc., to show you how those skills relates to what we just learned. Okay, so we're going to keep doing it over and over and over progressively as we learn more about the programming language. But for now, we don't know anything. So here's what I'm going to do with you tonight. I'm going to start with one program. I'm going to show you one Raptor program. So it's a flowchart. Okay. It's going to be very simple, very trivial program. I'm just going to introduce, I think, three instructions, okay, to actually have a program that does something. But the core of the program is just going to be, I get some data from the user. So I get two numbers, X and Y, from the user. I put them inside my program. Let's say this is my program. It's going to compute a formula, and it's based on X and Y, and it's going to give you give me a result, display on the screen a result. So this is what my program is going to do. It's going to read two integers, two numbers from the user, process them, compute a certain formula with them, and the formula is going to be basic, arithmetic, nothing fancy, and then output the result. Okay, so we are not trying to go ahead of ourselves and start teaching Raptor in details or programming in details. No, we just need a very simple program, something a little bit more than hello world, and so that we can illustrate those programming skills on something concrete. Okay, so here's our code. So flowchart, Raptor flowcharts look like this. Okay, they always start with a bubble named start and end with a bubble named end. Okay, you can see here arrows between the different elements that are vertical, that go down. So this is a flow of the program. We are going to talk about sometime the execution flow of a program. So here the execution flow is easy. We get started at start, appropriately enough, then we go to the next statement, and we go to the next statement, and we go to the next, and then we reach end, and we are done. Okay, so trivial flow of execution, very simple program. Okay, what does it do? Well, besides start and end, which are just there like placeholders pretty much, we have 1, 2, 3, 4 statements. Okay, the first two statements in Raptor, they look like a parallelepiped, okay, with an arrow coming into the right. Well, remember when I told you our program is going to read value for X and Y, and those values goes inside our program, and then our program output, a result based on values of X and Y. Well, I already used this kind of notation. If this represents my program here, you see that the arrow coming from the left represents input, and the arrow coming out from the right represents output. Well, in this case, this is an input statement. That means that it's going to, if we look at the first one, it's going to display on the screen a message to let the user know what we want them to type. Okay, so the message is between double quote, enter value for X. That's what's going to be displayed on the screen. And then the getX that you see here is there to remind us that we are going to read something from the user, allow them to type on the keyboard, and we are going to store that in variable X. Okay? Same thing for the next statement. Enter value for Y is going to be the message displayed. Then get Y means that we read the value for Y from the keyboard and we store it in a variable named Y. So we have those variables in memory. You can see them as, you know, little containers. And if the user types, for example, 5 when prompted to enter a value for X, then the value 5 will be stored in variable X in memory. And then if I type 10 when you ask me about Y, then the value 10 will be stored in memory in the container labeled labeled Y. Sorry. So that's for the input part. Now we're going to have, at the end of the program, some output. So again, okay, here's a symbol for output in Raptor. That's really similar to what I use in my previous diagram. Okay, so the output statement here is abbreviated with a put, P-U-T. Okay, so get is to get data, put is to put data on the screen, and then you can follow put by different things. You can say, for example, put hello world. That's what we did last week, right? When we were just testing Raptor, we had a little program that we wrote, and we used the put statement, and then an output statement, and then we specified a string. So strings, character strings, are always boxed by double quotes, okay? And inside those double quotes, what you put is the character that make up the message you want to display. Well, here we're going to do something different. We do a put, and then we have result. So you can notice here that we don't have double quotes again around result. So the word result is assumed to be the name of a variable. Well, wait a minute. We talked about a variable X here. We talked about a variable Y here. We never talked about a variable result. Well, I wanted to explain the input and output statements because they are really easy before we go and finish with the middle statement, which is where this variable result is going to be created, and we are going to put a meaningful value inside of it. So let's take a look at the middle of the code now. This box, without arrows to the right, without arrows to the left, is actually an assignment. An assignment means we are going to take a value, store it inside a variable. Or maybe, so instead of doing something like, for example, X is assigned 5, okay, that would be an assignment. Maybe the assignment is not as trivial. Maybe the assignment has an expression that needs to be evaluated. So I could say something like variable X is assigned 5 plus 2. Maybe this expression that I use to compute the value I want to assign to that variable, maybe this expression uses other variable, 5 plus y. All of this is valid, okay? So you can assign a value, you can assign an expression, an arithmetic expression that has only values in it. You can assign an arithmetic expression that is using both values and variables. Sometimes when you write a value like this, it's called a literal. Okay, so this would be an integer literal. If I do something like put hi, double string here, so the put statement is like this. Okay, this here is also a literal. Here you go. This is a string literal. So a literal means actually a constant, something that you wrote actually inside the code. Okay, so I wrote the value 5. I wrote the value string that says hi. All of those are literal. They are constant. You'll hear both terminology. Okay, we'll get into that in more details when we actually get into Java. Okay, Raptor is very lenient with syntax, so we don't need to be completely strict about the terminology yet. But as soon as we get into Java, yes, you're going to have to be used to that vocabulary. But we'll have time to get there. I just want to introduce things early so that you have time to get used to them, right? So what are we doing here? Well, in this case, our variable is named result. It's not X, it's not Y, it's result. And result is assigned, this is what this arrow here means, is assigned a value. This value is not just a simple value, it's a whole expression. And this expression uses both integer literals, like in this case 5, okay? But it also uses variable. So I do 5 multiplied by y plus x. I'm reading it backward, okay, because I started writing the 5, but it's x plus y multiplied by 5, okay? We use a star as multiplication in programming language. I do not know any programming language that uses the lowercase x or the dot or even just a space, right? For example, 5y. Now, that never works in programming language, or at least the ones that I am teaching on a regular basis. The multiplication in a programming language is always the star, okay, or at least Java, C, C++, C#, Visual Basic, and a bunch of others. Okay, so that's pretty much everything that there is to know about this example, okay? I'm kind of like jumping ahead. By the time you watch the lecture video on 101, if you haven't already, and by the time you start watching the video on apprenticeship exercises, all of this is going to be trivial. If you haven't watched them yet, well, consider this as an introduction. We took a very simple program, and I explained line per line pretty much how Raptor works on this program. I think I skipped a part here, or maybe multiple parts. No, there we go. That's just one slide. So this is going to be the part, like I said here, that is going to interest us. This is the core of the program. Okay, this is just reading value input. This is just displaying a result. This is actually computing that result. Okay, so that's it for our first program. So now let's trace it together. Let's see step by step what it does. So I could run this with Raptor, and Raptor is actually very nice because, as I mentioned last week, you can select the speed of execution. You can make it very slow, and if you execute a program very slowly, you're going to see a green highlight around the statement that is being executed. So you're going to see each statement become green in turn, and step by step things are going to happen. And if you look on the left panel of Raptor, at the bottom of the left panel, you have even, as a courtesy, you have a list of all the variables the program is manipulating. And as the green light moves to the next step, the values stored in the variables are being updated. So Raptor is a great tool to trace a program, okay? So here's the good news. When you're trying to look for a bug, it's going to be easy because Raptor has that feature. Here's the bad news. Many of you, I know that already, are going to say, well, you know, to heck with it. If Raptor can trace, I'm going to use Raptor to do my tracing. I'm going to get good grades, and I'm going to look like I know what I'm doing for the tracing skill, and then I'm going to be able to move on to the next skill. Wrong. I want you to learn to do this in your head. Why? Because ultimately, you cannot use a program to write programs for you. So eventually, down the road, down the list of skills, you're going to find yourself having to do things yourself without all of those fancy helper tools, okay? If you do not integrate, again, if you do not integrate the tracing skill in your own head, if you do not have a correct theory about what statement do, if you don't have a correct model of what happened in memory when you execute specific statement, and if you're not capable to just stick to it and do things step by step, you know, rigorously, there is no way you're going to be able to program. So you have been warned, okay? I know that there's this temptation to just let Raptor do it for you. Don't let Raptor do it for you because Raptor won't be able to take the exam for you. So that would be a very, very bad idea. So let's do it by hand, okay? Let's do it like I want you to do. We are not going to run this program on Raptor. We are going to simulate what is happening using just our brains and our understanding of what statements do based on, you know, what I explained on the previous slide. So let's take a look. Start. Easy enough. This is where the program starts. It doesn't do anything specific, okay? Now, every over statement is going to make something happen, either on screen, or even reading from the keyboard, or in memory, okay? Each statement is going to have a side effect. When you execute the statement, something is going to happen on the screen, something is going to be read from the keyboard, or something is going to be assigned in memory. That's what statements do, it's really like a limited set of possibilities if you think about it, okay? A lot of students, when they learn just to program, when it's the first time they learn to program, they feel a little overwhelmed. There are just so many ways I can write things. There are so many programs I could write. How do I know which one is right? Well, you don't attack the problem this way. Think in terms of there's just so many things a computer can do. There are few things a statement can do. Okay, once you understand that, it's like understanding how to use a hammer. Once you understand how to use a hammer, you can nail down vertically, you can nail it horizontally on the wall. You can do everything that entails pushing a nail into some material, okay? It would be stupid to just try to teach you to use a hammer by teaching you all the possible angle you can hold it and then all the possible situation. No, once you understand what the tool does, you can apply it, right? Same thing here. Once you understand what an input, output statement, and assignment statement do, and there's not that many of them. There are like 6 statements maybe in the whole of Raptor. Once you understand those 6 things very thoroughly, then you're good. Then you're ready to start applying them. And then there's a million of ways you can apply them, right? But that's going to be okay as long as you know what you are doing at every step of the way. So that's exactly what we're talking about here. Know what's happening. So what happens on screen and what happens in memory when we execute an input statement, and more specifically when we execute this input statement. So let's take a look. First thing that happens is going to happen on screen. Okay, screen. When I talk about screen, I should really talk about console or something like that. It's really both the screen and everything that's displayed and actually everything that's entered by the user. So we have our message here that's going to be displayed, right, on the screen. This is supposed to be representing a screen, and this is supposed to be representing a keyboard, and this is supposed to be representing a user. So the get statement, the input statement, is going to display a message on the screen, and then the user is going, using the keyboard, to enter a value. In this case, we say the user enters value 5. Okay. What happens next? We're not done with this statement. Okay. We display a message, we read a value from the keyboard, the user types 5, so we read 5, and then we store this value inside the variable x. Okay. So how do we keep track of this? Generally, I ask students to use, you can use Excel if you want, you can use a table in Word, you can use just a piece of paper or a napkin where you make a sort of table. Okay, it doesn't matter. But what I want you to do is to have a table where every line of the table is going to represent one line being executed in your program. Okay, and there is a little mistake here. Let me correct this. I apologize. There we go. There's a little mistake here. This is not line number 1. This is line number 2. Okay. I've numbered the statement. I started at 1 with start. So that means that here, line 1, statement 1, really nothing happened in memory. So I didn't have an entry in this table. But line 2, something is happening. So I'm writing down line 2 is executed. Okay. And then I'm going to make one column for every variable in my program. And in this case, I do have only one variable so far in my program. This is a variable x. So I have a column with variable x, and I say when line number 2 is done executing, this is what happens in memory. Variable x contains 5. And that is tracing. So what's the trick with tracing? People go too fast. That's one of those main reasons for which people have students have problem learning tracing, is they want to go too fast. They read code, they glance at code actually, and they say, well, I see what this is doing. This is reading x, putting it into x, then y, blah 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 blah. And they can explain to you in 5 sentences what the entire program is doing. However, it's not scrupulous enough. It's not rigorous enough. Okay? If you really want to understand what a program does and not make mistakes as you're reading it, you need to keep track very rigorously of everything that's happening at every line. And the best way to do that is to use something like this, a table, okay, where you keep track of every line that executes and its effect on all the variables that are in memory. That's the only way. So yes, it's tedious, and yes, it takes time. The good news is that the more you do it, the better you get at it, the faster you can go through it. So practice makes perfect in that case, definitely. You are going to get dividends on your effort in terms of your tracing skill augmenting. It's a very easy skill to learn. Just put in the work and you'll be very good at it. But the thing is that people get bored while doing this. They want to jump to shortcuts. They want to go directly to the end of the program, and this is why it doesn't work for those people. If you try to take shortcuts, then you completely defeat the purpose. The purpose for tracing is not for you to make an essay, to write an essay on what you think the program might be doing. The purpose of tracing is for you to emulate, to do the job of a computer and execute things step by step rigorously. Computers are really good at that. They don't get bored, and they are really reliable. Human beings, not so much. We get bored, we make mistakes, we are not reliable. So part of learning how to trace is to learn discipline, to learn to focus yourself on the task at hand and not take shortcuts, not skip lines, not assume things as you are really trying to emulate what the machine is going to do with your program. Okay? If you follow those guidelines, that should be easy. But there is still some skill, obviously, to gain. Okay? New skill to develop. What about line number 3? So the bug was corrected here. You see line number 2 now is on the slideshow. So I keep my line number 2, and the result was to create and assign a value to variable x. Now, when I execute statement number 3, line number 3, same thing happens, okay, except that the message now is enter value for y. So we display a message on the screen. The user uses the keyboard to enter a value. This time the value is 10, and then the input statement store this value 10 inside a new variable. So I add a column to my table. The name of the variable is y. So I write here that line number 3 executed, and at the end of line number 3 executing, I expect y to contain the value 10, which was provided by the user. So same thing as the first input statement. We keep going. Now this line here, line number 4, statement number 4, little bit more interesting, little bit more tricky. The variable named result is assigned, this is what this arrow means, the result of computing, evaluating this expression. And that's the key of it. If I had just a value here like 42, I would just take the value 42, assign it to result. And that's it. I store 42 inside variable result. But here, I have some work to be done. Okay, there's an entire expression, and this expression even involves other variables. So how do I evaluate this expression? Or more to the point, how does Raptor evaluate this expression? That's what I need to replicate here, what Raptor does. Not what I would do, not what I think Raptor should do, no, what exactly Raptor will do with this expression. I need to know that. So after module 101, 102, 103, you'll be comfortable with that. Here I'm going to give you the answer. I'm going to show you how Raptor is handling this kind of expression. Well, Raptor starts with certain operators. We have a plus and a star operator here, so addition, multiplication, okay? The multiplication operator, you can view it as being above the addition operator. It has priority, okay? So Raptor starts by saying, well, I have two operators here. This one has priority over the other one. I'm going to start evaluating this. So this operator has two operands, okay? I'm using here vocabulary that should kind of like ring a bell from even just K-12, you know, mathematics. So just let me know if I'm confusing somebody, but that should be relatively easy. Once we identify that we want to evaluate this first, right? What we do is we realize that there is one variable in this expression, y. So y needs to be evaluated by itself. I cannot work with y. I can work with the value inside of y. So I look up in my memory and I find that variable y contains 10. So I replace y by 10. So now I'm left with evaluating this multiplication, but I have, for both operands, I have values. So I can go ahead and compute the result. 10 times 5, 50. Now this is what's left. What's left is one operator, okay, and it's two operands, okay. This is addition. There's only one operator, so I don't have to worry about priority. I'm just going to go ahead and compute its result. But wait a minute, there's a variable here. So what's the value of the variable? 5. Okay, so I take care of that first. then I'm left with 5 plus 50. I can compute the result of that. This is 55. And that is how an arithmetic expression is evaluated in Raptor. And modulo some peculiarities, like difference in the priority of operators and stuff like that, this is pretty much what happens in any programming language. But some programming languages have different priorities between operators. Some programming languages like Java actually do something a little tricky with the order in which they evaluate. Some go left to right, right to left, whatever. Okay, so there's more on that topic, okay? But we are going to go back over that when we study module 201, okay? Because this is really syntactical. This is really about the syntax of a language. So all the time we're going to work with Raptor, I need you to be aware of the priority. For example, multiplication comes first before addition. But all of the specific rules about, precedence, associativity, we are going to study them when we deal with a full-blown, full-scale programming language, that is Java, okay? So for now, just knowing that multiplication comes before addition is enough for us. And you see how we come to a result. And then this result is assigned to a variable result, okay? So this is what we're left with. When I execute the last part of this statement, which is assigning 55 to result, then I'm going to note that line number 4 just got executed. It did not modify X. It did not modify the value of Y. So when things are not modified, I leave those cells in the table blank, okay? So just so that I don't have to write all the time 5, 5, 5, 10, 10, 10, etc. So I leave blank whatever in memory I do not modify, and I write down 55 in a new column that is there just to represent what the variable result is storing. Okay? And that's the third step of my trace. Okay, line 1 didn't do anything, so this is the third step that I had to really account for in my trace. What's next? A put statement. So this is the first time we're using a put statement. What does it do? Simple. It just takes whatever you want to display after it, like in this case, variable result, and it's going to display it. So when you ask, I want to put result, this is a variable. It's evaluated into whatever it contains. So 55. So really what you are writing here is put 55. Okay, put whatever is in result. In this case, we want to put 55. So 55 is displayed on the screen. The user can see that. Everybody is happy. Our program has done its job. And then I go to the next step, and this is the end. The program stops there. We displayed 55 on the screen. Okay. I really try to go slow through this first programming skills. The other programming skills are going to be shorter to explain. But I really wanted to go slow here, because when you do tracing, you have to go slow as well. You have to force yourself to go slow. And I know that in an exam or a quiz, you want to go as fast as you can because you are stressed, you are wondering about the time that you have left, etc. But here's the thing, you can go slow and do it right, and then because you do it right multiple times and you practice, you end up being good at it and you end up being able to go fast. Or you can try to go fast without developing the skill first, and generally that doesn't work so well. So heed my advice, okay? Yes, it's going to take some time at the beginning. It's a good idea for you to take our apprenticeship exercise, okay, that are already written for you, and for example, try to trace them. That's very good practice, okay? So this week, go back and revisit our apprenticeship exercise, A01, A02, A03, etc. Okay? Implement them in Raptor. Okay? And you should have time to do that because we don't have problems. We don't have JavaBat. We don't have a lot of practice exercise. So this would be a great practice for this week. And then, after you implement them in Raptor, take a piece of paper, try to trace them by hand on paper, and then run Raptor to see if you got it right. Okay, and if you didn't get it right, run Raptor slowly, use that little slider to make it execute slower, and look at step by step your trace and the trace that Raptor provides, and try to figure out where you went wrong. Okay? And when you figure out where you went wrong, don't just copy what Raptor does, just try again to do the exercise on your own without Raptor first, and try to find out what you did wrong and fix it. Once you get that done, run Raptor again to verify that you were right. Okay, so this is actually very easy and very good practice for tracing skills this upcoming week during Module 101. Okay, Second, sorry, I'm going ahead of myself. Before to go to the second programming skill, some advice on tracing. So I already pretty much mentioned all this. Just go over the slide quickly. Be extremely rigorous, go slow. Do not narrate what you think the program ought to do. It's really easy and really tempting for people to just take a glance at the program and summarize the whole program. This is also very error prone and that has nothing to do with tracing. So this kind of reasoning will have a place in programming. You will rely on it in due time, but this is not tracing. So when I ask you to trace something, really go step by step, go slow, go very rigorously. Follow scrupulously each statement based on what you know they are doing. So the first thing is learning what an input statement does in detail. Okay, so an input statement displays a message, then reads a value from the keyboard, then assigns that value to a variable. That would be my definition of an input statement. What does an output statement do? Evaluates, if needed, what has to be displayed, then display it. Okay? What does an assignment statement do? Just a regular box. Evaluate what has to be assigned, and then assigns it. Okay? So, all of this, what I wrote here, is pretty much what I lectured about over the last 10-15 minutes. This is your knowledge base. This is, this assignment does that. This assignment does this. This assignment does this. If you don't know that, you cannot trace. You have to know that. You have to make sure that you really understood, you know, what each assignment does. So if you have any doubt, any question, use your critical thinking abilities, okay? Make sure that you do not just memorize one thing from the textbook or the video and then go with it without trying to question it. No, question the statement until you really understand what they are doing. Once you know what the statement are doing, then it's just a matter of being disciplined, being able to apply things like almost mechanically. All right. So we're done with tracing. Second skill. This one's going to be easier. I mean, easier to explain at least. Implementing. All right. So when I talk about implementing something, I'm going to always assume that we have some requirements. So watch out for this word. We're going to use it a lot, okay? And you are going to use it a lot in IT. Requirements are a goal. This is a description as accurate as a client can make it without knowing how to program of what they want, not how your program is going to achieve this. No. The requirement is not about how. Requirement is about the end result, what the program is expected to do. Okay? And always think, when you get requirements, always think that the person who wrote the requirement is actually somebody who doesn't know anything about programming, maybe somebody who doesn't know anything about IT. So they are going to write requirement in plain old English, and this is going to be often ambiguous, and it's going to be often under-specified and sometimes over-specified in other area. Requirements are not perfect. Requirement analysis is actually one of the steps of software engineering, software development, and it's arguably not the easiest step at all. Okay, it comes way before programming. It's outside the scope of this course, but I'm trying to impart on you the idea that yes, requirements sometimes need work before we can transform them into programs. That's the job of a software engineer. Okay, so for now, we'll just assume that we have decent requirements. I will do my best to give you requirements that are not ambiguous, okay? But as we progress through the course, some of them might become a little bit ambiguous to see if you're capable to actually analyze them a little bit. Nothing fancy. We're not going to do software engineering in this class, but I want to pretty much get you used progressively to realistic situation, okay? This requirement, for example, write a program which reads two integers from the user, adds them up, multiplies them by 5, and then displays the result. Okay? This requirement is a little bit ambiguous. We'll see why in a few minutes. But I did that on purpose because I wanted also to show you how to debug. Okay? But even something as simple as this can be ambiguous. So you have to learn to be really careful about how you read the requirement, be really detailed. The devil is in the details here again. So based on those requirements, when you have to work on an implementation question, we will assume that the requirements were given to you, and furthermore, we will assume that somebody already took the requirement and designed a step-by-step solution. So take a look at this. It's almost like a computer program, right? Except that it's written in plain good old English, so it's informal. It's not a formal computer program. It's like having a fragment of text, explaining an equation as opposed to as a mathematical notation of the equation itself, okay? So it's not the end product, but it's very step-by-step. It's very organized. It's structured almost like a program. You need to do this, then this, then this. So it's a sequential list of statements. Instead of writing the statement in Java or Raptor or any programming language, I just try to write them in a very informal manner using plain English. Okay, so read an integer value from the user. That would be our get statement in Raptor. Okay, store it in variable X. Well, actually, the get statement can do this and this. Okay, read the integer, then store it. Read an integer value from user, store it in variable Y. That could be another get statement. Then store the result of X plus Y times 5 in a variable name result. That looks like an assignment statement. And then display the variable result. That looks like an output statement. Okay, see what I've done here? Given a solution, I already have my solution. That's really important, right? Implementing is not about problem solving. Implementing is somebody already did the problem solving for you. Somebody already designed a solution that satisfies specific requirement from the client. And you are in charge of implementing this design into actually a computer program using a specific programming language, in this case, Raptor. Okay, so what I did by hand, you can see the result in the next slide. It's obviously the same program that I use for my for illustrating the previous programming skill. So you can see that this is pretty much following this design recipe, except that we do something more besides just reading the integer and storing it in X. We also display a message here, enter a value for X. So arguably, we should have a line here that says display prompt blah blah blah, telling the user to enter value for X between quotes. Okay. But this is pretty much what implementing is about. So anytime you have an exam question, that's going to be implementation. And I told you already that the exams are going to have separate questions, and each question will test one of the programming skills. So typically for our first exam, we will have a tracing question. I will give you a piece of code. Mitch actually will give you a piece of code and will expect you to produce a trace table, or maybe to just tell us what is the outcome, the output of the program at the end. Okay, so assuming that you do your trace table, you don't have to turn in your trace table, but you have to do it on paper or however you want in order to figure out what the outcome of the program is. Okay, so this would be a tracing question. An implementation question, we would give you something that is maybe a little less structured than this. Okay, because this really looks like pseudo-code. Some of you might have heard about pseudo-code. Pseudo-code is when you use a pseudo programming language that's based on English words and sentence to summarize, an algorithm, a program. So we are not going to probably give you a pseudocode that is that detailed, but we would give you a paragraph where pretty much every step of the program is there. You just have to learn to read the paragraph and translate it into a Raptor flowchart. So that's what implementation is really about. It's about translating a pseudocode or a description in plain English of a solution of a program that's already solved into code in a specific programming language. Again, it's not difficult. It's not difficult, but you have to, again, know your language. You have to know what this statement in Raptor does, what this one does, what this one here, the assignment, does. If you don't know that, there's no chance you can actually implement anything or trace. So once you know your statement, then the key is to scrupulously follow the pseudocode read very carefully the description, the step-by-step description of the program in plain English, and be able to map that to the right language construct. So if I go back to slides, this is exactly what I did there. And sometime, for example, one step of that solution maps to one construct in your language. Easy enough, right? It's pretty much transliteration almost, okay? But sometimes you are going to have to realize and understand that two of those steps of the solution map to one construct in your language. Okay, Raptor has one construct that displays a message, reads an integer, and stores the value in a variable. Java doesn't have that. Java is capable to display a message with a statement, but then it needs to use another statement to read a value and store it in a variable. Maybe a third language that I don't know about has to have three statements to do this. One to display, one to read, one to store. I don't know. But the bottom line is that if you know your language, then you are capable to do that mapping between the plain English description of the solution and actually its implementation in that programming language. Okay? So again, a relatively easy skill to learn. The more effort you put into it, the more practice you put into it, the better you get at it. So that's really rewarding, actually. You work hard, you get immediately better at something, you get better grade. So don't skimp on the practice, okay? It's going to be something that's going to be definitely tested in all of your exams. You will have a tracing question, you will have an implementation question at every exam. Next programming skill, testing. This is a huge topic. Okay, if you ever heard of some people you know that work in IT that are in quality assurance, also referred to as Q&A sometimes, quality assurance testing, software testing, professional, this is a job in and by itself. Generally, in a company, there are going to be people writing code, people testing the software. However, over the last decade, testing has become something that programmers also do when they write the code. And actually, in some companies, the programming methodology that is used says, write your test first, then write the program that is capable to pass those tests. Okay? So, bottom line is that testing is an integral part of programming. It has become an integral part of programming. Programming is a relatively new discipline. Okay, it evolves a lot, and over the last, I would say, decade or 2 decades maximum, testing has become a prominent drive actually in the software industry. So no matter a little of a program you write, you might have to do some testing. Plus, the advantage of testing is that testing is a way to validate what you did. So what happens a lot when people learn to program is that they would actually read the requirement and they would type, for example, 50 lines of code or 2 pages of flowchart if we use Raptor. And they would just be obsessed with, I have this idea in my head of how to solve this problem, and I just need to map it out in one big step. And generally, that's catastrophic. They spend maybe half an hour writing the code, then they spend 5 hours trying to figure out what is wrong with their code. So testing helps you with that. Testing is the way we're going to use it as a tool to learn how to program well. Testing is going to allow us to set ourselves small goals, intermediary goals. So I have 1 page of requirement to satisfy. I'm not going to take all of this in one shot and write 1,000 lines of code before I even compile. No, I'm going to actually identify small things in the requirement that are easy. And I'm going to just implement one at a time. But every time I implement one, I'm going to also scratch my head to find a way to validate that the little piece of code I implemented, maybe 5 lines, 3 lines, actually does what the requirement, what this part of the requirement asks for. Okay, that's going to be done with testing. Let me illustrate. So first, before to illustrate, I was just mentioning that a lot of students, tend to write a lot of code in one shot and then hope for the best that it works. Well, there is an underlying question that's part of learning to program. When is your program done? So when do you know that your program is done, that you have satisfied the requirement, that you're going to get a good grade, that you're not going to get fired, depending on whether you are still in university or you are actually working for a company? So some students think that when it builds, it's done. So the concept of building a program, I didn't introduce it yet. Let me try to explain it briefly. When you enter a flowchart in Raptor, automatically Raptor builds your program. View it as prepares it to be executed. Okay. Now, over language like Java, for example, when you type a program in Java, it's just a text file. You type text in a file that's following the Java syntax, and then what you do is you feed it to Java. Java is a tool, Java is a command. Java is going to analyze what you typed in your text file and produce something that can execute. Okay? In the case of Java, it's called bytecode. Okay? So you see how Raptor is really an interpreter, so I'm skipping a step here, but Raptor is really capable to build on the fly and have your program always ready to run, in a matter of speaking. I'm simplifying a little bit. Other languages like Java use a specific tool, another program, to read text files with code in them and transform it into something that can execute. It can be a bytecode, it can be a .exe file, it can be all sorts of things. Okay? So that's the idea of building. The idea of building is that when you do programming with Java, if you make syntax errors here, like you forget to close the parentheses, you forget a semicolon, any syntax error, then the build is going to fail. Java is going to tell you, I do not understand what you're trying to say here. It looks like you are missing a parenthesis, but I cannot fix it for you. You have to write it correctly. Okay? So this is why some people think that when they are capable to write, for example, one page of code, and the code is accepted by Java, that means it's working. Not necessarily. Okay? If I write something like x equals 42, this is correct syntax in Java. Okay? Semicolon, actually. That assigns value 42 to variable x. So it's equivalent of Raptor x arrow 42. Okay? This is Java on the left, Raptor on the right. But if I write x equals 43, from the perspective of the programming language, it's correct. It's perfectly valid, but maybe it doesn't make sense because x was supposed to be 42 and I just made a typo. That would be a runtime error. That would be an error when I run the program. Syntactically, the program is correct. It's like saying that if I tell you, for example, the sky is I don't know, whatever adjective, the sky is soft. Is it a correct English sentence? Yes. I didn't make any spelling mistake. Grammatically, I followed English grammar. It's fine. Does it make sense? Not quite. Okay? That's the difference. The build step is your program syntactically correct? So we check the syntax and the grammar. If it is, that's great. That's a good start. Doesn't mean that the program is correct. Okay? So we still need to test it. We need to see if the program does what it's supposed to do. How do we do that? By running it. Okay? So in the case of Raptor, you don't have to worry about build time mistake. Like I mentioned last week, Raptor will simply not let you make a syntax error. It's completely drag and drop. You drag and drop a statement where they belong in the flow of the program, and it will not let you make a single mistake. So that's kind of why we start with Raptor. It's because it makes our life easier. It eliminates a whole category of mistakes that when you just learn to program, you do a lot of. Okay, people do a lot of syntactical error and grammatical error when they just learn a new programming language. So we are not going to deal with that for 3 weeks, and then we will learn it with Java, as I explained last week. Now we still have to make sure that our flowcharts do what we think they're supposed to do, what we think we told them to do. So how do we figure out if the program works? Do we run it on one sample input? Is that enough? Do we need to run it on 50 sample input, on all possible sample input, all possible numbers that you could feed to X and Y, for example? Well, that's the key. That's the key to learning how to test. Okay. Generally, we try to find the minimum amount of input values that are sufficient to give us confidence that the program is working. Okay, so if my program takes X, Y, does something with them and produce an output, okay, my tests are going to consist of values for X, values for Y, okay, and then the expected output of the program. So knowing what the requirements are, I base my test on what the program is supposed to do, okay, the requirements. So knowing the requirement, if I give 5 and 10 to my program, I expect this, whatever this value is, okay. That's what a test is, okay. Now, what do I use as sample input? There are different ways to build tests. The first one, we always do it a little bit. It's called exploratory, like an explorator, right? Exploratory testing. That means I play with my program. I just wrote my code, and I'm going to enter values for X and Y. I don't know yet what my tests are. I'm not going to write down those values in a table like that, X, Y, and expected output. I'm just trying to get a sense of what values are useful, okay? For example, if you had an expression that is, X divided by Y, if your program computed X divided by Y, X and Y being provided by the user, if you divide something by a value given to you by the user, make sure it's not 0, because division by zeros, computers cannot do that, okay? That would be a bug. So that would be part of exploratory testing. I'm trying to figure out what values make sense, okay? Like I said, you rarely will cover every possible situation. Because for a trivial program, like for example, if I ask you, give me a number between 1 and 3, give me a number between 1 and 5, okay? And that's the input for my program. How many possible numbers you have? It's really reasonable, right? You have like 15 total possible combination of numbers, and you could test all 15 of them. Now, if your input is a number between minus 32,000 and plus 32,000 for X, and then same thing for Y, 64,000 sum squared, that's a lot of tests to write. Nobody wants to do that. It will be taking more of your time to write the test than to write the code or even test it, thoroughly. So we don't want to always go with all possible situations. Okay? We want to find the subset of tests that is enough to give us confidence that things are working without necessarily going over every single possibility, because that, in practice, is rarely feasible. And this is why I say, do I make sure also that my set of input value, my set of tests is as small as possible? Yes, definitely. Okay. So do I make sure they cover all possible situations? No. Do I want the test to be as small and not redundant, as small as possible and not redundant? Yes. Okay. Let's take a look at the rest. So very important, testing is not trivial. That's the first non-easy skill that we are discussing about programming. It's sort of the last, but this is the first one. There's a big leap between tracing, implementing, and then testing. So it's an art all in by itself. Some people just focus their entire career on learning to do that. We are not going to try to turn you into professional quality assurance people. We are not going to turn you into professional tester. The only reason we use test is because using test teaches us how to program well. Okay? That's the only reason we are talking about tests in this introduction to programming. So more specifically, what does that mean? That means that tests allow you to do a few things that are really useful when you learn to program. For example, express requirements in formal terms. Okay? If I give you, for example, write a program that reads 2 integers from the user, add them up, multiply them by 5, and display the result. Okay? I can explain this requirement in terms of a test table. So I say, here are my input, here's my expected output, okay? So for X and Y, let's say that X is 3, Y is 5, okay? So the requirement is write a program which reads 2 integers, so 3 and 5, from the user, adds them up, so 3 plus 5 equals 8, and multiply by 5. 5 times 8 is 40. Okay, so based on reading the requirement, and that's important. You can write most of your tests, not all, but you can write a lot of tests just by reading the requirement without writing a line of code. I can devise my first test, and this will help any programmer understand what I mean in my requirement. Furthermore, I can go back to my instructor if I am at a university, or I can go back to my boss or my client if I am in a company, and I can tell them, is that what you meant is that what you meant by your requirement? Because we know that requirements are ambiguous, okay? They are written by people that don't know necessarily about IT or programming. They are written in plain English. English, like any other natural language, is ambiguous, okay? It's not as formal as mathematics or a programming language. So I can go back to my client and tell them, look at my list of tests here, okay? These are tests I wrote based on your description of what you want the program to do. Does that match? Is it what you meant? Okay, and then they can validate. They can say, yeah, this test really does what I would expect the program to do. This one too, this one too, this one too. Oh, this one I don't know. What did you probably misunderstood something here. Okay, so tests can be used to express requirements in a more formal manner. They allow you to understand requirements and talk about requirement. Okay, tests also help you make sure that all the path, the execution path of your programs are tested. So what does this mean? Well, we have so far a very simple program to deal with. So you are going to probably understand this by a little better by module 103. Okay, 102, 103, we're going to discuss about constructs where the execution path in a program can change, and then that's going to be really what's going to help you understand what I mean here by this bullet item. But to give you an idea here, right now in my program, I always go from start to the next, to the next, to the next, and then I reach end. Okay, that's called one execution path. It's a way to run through the program from start to end. And there's only one way to do it in this program that we have been using as an example. Now, if I add something like that, if I add a symbol in my flowchart that is a diamond, and there is a question here, you know, is this variable equal to that value or whatnot? And then here and here you would have two different statements and then the end statement. This program would have clearly two different execution paths. Depending on the answer to that question here that I check, I could execute this code or I could execute this code before to reach the end of my program. So that's what we mean by execution path. Again, just an introduction for now. In module 102 and 103, we are going to cover the traditional execution path, okay, meaning conditional and iterative, and we are going to discuss how we can test them, okay. A test is also a way to document a bug. For example, let's say that you have a program that asks you for value X, value Y, okay. This program creates an output. Let's say that I give 0 for Y. So I'm talking about a different program than the one we are playing with, okay? It uses a different formula. For example, it uses X divided by Y, and it displays the result. Well, let's say that I enter 0 for Y. Division by 0, not so good, right? So my program here is going to say, I cannot do that, there is a mistake, you know, imagine a fireworks, explosion, smoke coming out of the computer here, whatever, okay? So the program is not going to be able to perform its duty, it's going to tell me there's a problem. So now, I have understood that when I enter 0 as value for Y, that creates a bug. So I'm going to modify my code so that it accommodates this. Maybe instead of crashing, the program is going to display, I'm sorry, I cannot process this set of input values for you. You know, Y is 0, I cannot do that. Try again, and ask me again to enter, you know, something. Well, that would be me discovering through exploratory testing, for example, that 0 in Y is a bad idea. Then fixing the program so that it warns the user instead of crashing and allows them to enter a different value. And then to remember that Y equals 0 is a problem, I would devise a test. I would say, this is what I expect, okay? If X is, and X can have any value here, so if X is 3 and Y is 0, then what I expect is an error message, and try again. And I would test that by hand, okay? I would enter 3 and 5, I would make sure that the program gives me 40. I would enter 3 and 0, I would make sure the program display an error message that I told it to display, and invites me to try again, okay? And then sometime when you write a formula like this in your program, because you have been doing it so many times, you know that this means that there is possibility of a division by 0, so sometime you're just going to anticipate potential bugs. And every time you write this, you're going to say, oh, this can go wrong so easily. I'm going to add a test where Y is 0 and make sure my program handles this graciously. Okay? tests can be written on paper, which is what we're going to do when we use Raptor. Okay? And when I say paper, you know that I mean also an Excel document, a Word document. Or they can be implemented in unit tests. We'll talk about that way later. This is actually the professional way to do that, but we're not yet professional developers. We are going to do things a little in an ad hoc manner, kind of by hand with papers, etc., just to really understand the process and get the gist of it. And once we are comfortable with the process, the testing process, then you will be able to learn how to do professional testing in whatever language you want. Okay, but you have the concepts. So let's try to illustrate this. What were the requirements for our program? These were the requirements. So based solely on the requirement, I can prepare a test. So this is my test table for a program. The first part, all the input values, all the data the program needs to work. So in this case, two variables, X and Y. So two columns in the input part of my test table. Then what is the outcome of the program? So sometimes it's an output, sometimes it's writing something on the disk. What does the program do, pretty much? And there are two columns here. One, where I'm going to write down what I expect, based on the requirement, what I expect the program to do. And then a second column is what I observe. And I'm going to show you how I use that one, okay? So my first and unique test for now is if I give the value 5 and the value 10, I expect the outcome of my program to be 75. 5 plus 10, add them up, okay? Then multiply by 5 and display the result. So I would expect 75 to be displayed. All right. So now what I do with my test, I run my program and I make sure that what the program does, actually, what I observe the program doing when I run the program, matches what I expected the program to do on those input value based on the requirement. So I'm executing the flowchart in Raptor, it gives me 55. How come? Well, because it did 5 plus 10 times 5. And you remember how this expression was evaluated, right? 10 times 5 is 50, so 5 plus 50, which is 55. Okay. So this is going to happen very often. You think your program is doing something, you always write it in good faith. You always write a program to satisfy the requirement. Nobody writes a program to be a bad program, right? But however, you're human, you make mistakes. Like for example, here you forgot about the priority of the multiplication over addition in Raptor, and then you get a discrepancy. You get a difference between the expected behavior, what you wrote your program to do, and what it actually does when it runs. And this is very, very common as you learn to program. This is why we have tests, because it's so common that we need a process to catch all those mistakes and fix them before we ship the program, before we turn it in to the TA for grading and the TA gives me a 0, or before I turn it into my boss, who demonstrate it to the client and crashes in front of a PowerPoint presentation showing the demonstration of the program to the client, and then he comes to me and he fires me. Before those things happen, we need to be sure that we did a good job. And most of the time, we won't. We won't the first time around. So we write some code, a little bit of code, we test it, we validate it, we test, and then we make sure it works. And we keep doing that, we keep adding tests until we are really confident that it's working. And only then we turn it in, we submit to the client, we submit to our boss, and so on and so forth. Okay? So don't let yourself be caught into, well, I don't know what this is about, this 55, I wrote the code and I know that it does, X plus Y times 5. You could repeat that to yourself in your head 50 million times. It's not going to help you figure out what's wrong. What's going to help you figure out what's wrong? Tracing. Stop thinking about what you tried to do and what you meant to do. Start thinking about what the machine is going to read, how the machine is going to interpret this code step by step, and that's tracing. So testing helps us uncover mistakes. Tracing will help us actually fix that. So before we go on to fixing mistakes, which is the next programming skill, advice on testing. Like I told you, this is not a course about testing, so there's a lot that could be said about software testing. We are just going to follow a few rudimentary rules, okay? And I'm going to give you those rules now, but we are going to repeat them and use them every module. So they are going to sink in progressively. But I want to give you an overview. The first rule that we're going to use very often is test boundary values. Every time a requirement tells you, write a program that reads an integer between 3 and 9, inclusive, okay? Every time a variable should have only values between 3 and 9. Every time there is a constraint that involves a variable having a value within an interval. How do you make sure that your program works within the intervals, but detects when there are problems, when there are values that are outside the interval? Well, there's an infinity of value after 9, there's an infinity of values before 3, and there are 6 values between 3 and 9. So if I test my program on 3, 4, 5, 6, 7, 8, 9, it's great. But so I can make sure that it works for all those values. But if the interval is large, it's not practically feasible. I'm not going to write 10,000 values. Plus, to make sure it works with those values, but rejects, the other values, I would have to write tests with all the other values, practically infeasible. So the rule of thumb that we use, at least for this course, is if the interval is between 3 and 9, if a variable should have a value between 3 and 9, like an input variable, you are going to test 3 and 9. These are the extreme boundaries of your interval, inclusive, right? So these should work. And then you are going to test the smallest, the first small value that should fail, 2. And then the smallest value that should fail at the other end of the interval, 10. So you are testing for an interval x, y, you are testing x minus 1, x, y, and y plus 1. Okay? It's not a magical recipe. Sometimes you will have to test value in the middle of your interval, inside your interval. But for most of what we're going to do in an introductory course, this is a minimum stuff to watch out for. Okay? Every time a program tells you, you are going to get a user value between 3 and 9, what if the user enters 4? It works. What if the user enters 2? Your program should do something about that. It should say, out of range value, I cannot compute the result, give me a valid value. Okay? The second thing, I'm going to start with this one. The second thing that I'm going to talk about is test for likely bugs. So every time we learn a little bit about programming, like next module, this module here this week is going to be 101. We're going to learn about data values. We're going to learn about expression, arithmetic expression. Then we're going to learn about conditional expression, then iterative expression. Every time we learn something new, we learn to do something new with the programming language, any programming language, we are going to also often discuss classic bugs, classic problems, okay? So you have to keep those in mind. And you have to write bugs to try to make sure that your program doesn't exhibit, you have to write tests. Do not write bugs, absolutely sorry about that. You need to write tests to detect whether your program exhibits any of the bugs that we talked about in the lecture, in the apprenticeship exercise, the practice exercise, okay? And then test all execution paths. I'm going to talk more about this one in module 1 or 2. Okay, really right now it's a little awkward for me to give you more information than what I already said because we haven't studied a if statement or a loop statement or something like that. So leave it at that for now. Next programming skill, debugging. So you wrote a test, this test failed, and now you have to figure out what mistake you made when you wrote your program. Okay? So it's always triggered by a test where debugging is always triggered by a test where the expected outcome doesn't match the observed outcome. And obviously there is one easy way that this can happen. If the expected outcome is wrong. So you read the requirement, you didn't understand the requirement, you wrote a test thinking that this test represented the requirement, and guess what? It's actually, the test itself is a mistake. So that's why tests are a good thing to share with other programmers, to share with instructor, to see, to let them tell you whether those tests represent the requirement, okay? If this was a course about about software testing, I would make the testing process much more difficult, and I would try to test your skills much more thoroughly in testing. Here, we are going to always have testing problems that are relatively easy, because it's just a way for us to learn to program, okay? But nevertheless, you could make mistakes there, so make sure that you double check that your expected value actually makes sense. And then if not, then that means that it's an observed value that has a problem. So the observed value is produced by your program, so your program has a bug, your program has a mistake. How do you go about fixing this? First step, identify. Identify the part of the code that is responsible for the problem. We are going to work with small programs in this introduction to programming, and I'm going to teach you and force you to write a little bit of code, 2-3 lines at a time, and test them thoroughly. 2-3 lines test, 2-3 line test. Why? Because if you do this, most likely, if a test fail, it's going to be found in the 2-3 lines that you just wrote. Not always, but most of the time. So that's going to make it easier for you to identify where the bug might come from. So you just put your finger on the part of the flowchart that is responsible for the problem. Then you need to understand why the program is doing something that you observed that is different than what you expected. There's no way to automate this. You're going to have to use your gray matter. You have to use your brain, okay? You have to understand why the code is misbehaving. So obviously you didn't write it intending for the code to misbehave. So your intention and the actual code differ. What is it most likely due to? It's due to a difference between what you wanted to do and what the statement you wrote in your code does. So this is where tracing skills are so important. Forget about what you were trying to do. Look carefully at the code and tell me, based on what you learned about Raptor, about programming in this class, tell me what this is going to do, what the computer is going to do with this statement. Trace the whole program if you have to. Figure out what the machine is doing. Once you understand what the machine is doing, then you can formulate a new hypothesis about how you should modify your code. Because obviously what you did, the machine interpreted differently than what you thought originally it would interpret it as. So now go back to the drawing board. Now that you know how the machine interprets this code and you know what you want to do, rewrite it so that it gets closer, the machine gets closer to what you want it to do. Okay? Then implement it. So this is where the implementing skill comes back. And then guess what? You test it again, because it's not because you fixed it that it's done, right? You wrote code thinking that you were doing well, and it didn't work. So now you write a modification. Why would it work? You are going to make mistakes. That's part of programming. So test again and debug again. So repeat this process, repeat and rinse until you get it right. What is important? Always understand what went wrong. Do not modify randomly things. Understand what went wrong. Increase your understanding of what the programming language, how the programming language interprets your statement, and use that to improve. Okay? I'll talk about that a little more in a minute. Let's take an example. Let's illustrate that debugging skill. So here's our program. Okay? We have a test, and we have a discrepancy between expected value and observed value. Who is responsible for that problem? Well, the first reflex might be to say, this is a statement here. The but statement is responsible for my problem. Why? Because the but statement displays 55 on the screen, and I don't want 55. I want 75. That's okay. That's a good first step. However, as you get into looking into your code more carefully, you're going to realize that there's no way to fix but result. But display the value inside result. This is nothing is wrong there, as long as result contains the right value. So hold on a minute. This is not what's responsible for the bug. This here is what is responsible for the bug. This assignment statement. Okay? So that would be the first step of identifying what part of the code is responsible. Sometimes it's trivial, sometimes it's a little bit more difficult, but you see the logic that I've used here. Okay? It's really common sense. And the more you do debug, the more you're going to acquire this logic. And trust me, you are going to spend a lot of time debugging. You might try to be lazy in practicing implementation and tracing and maybe even testing. I know some students are going to skip all sort of practice and hope for the best. That doesn't work, like I told you. But there's one thing that you cannot avoid practicing is debugging, because the least you practice the other skills, the more bugs you're going to have in your program. So the more you're going to practice debugging. I would prefer you to practice all of the skills so that actually you don't spend all of your time debugging. You make progressively less mistakes because you become better at tracing and implementing, okay, and testing. So try to balance out things, and you'll see that it works out pretty well altogether. So now that we know what part of the code is our problem, and based on what we learned in the lecture, readings, apprenticeship video, this is where you have to have that eureka moment, okay? Nobody can do that for you. This your brain has to do that, okay? You have to realize that what is wrong here is that I have a priority between multiplication addition, and the way I wrote my formula didn't help me compute what I really wanted to compute. The requirement we're talking about adding x and y together and multiplying them by 5. That was ambiguous. Do they mean multiply x plus y together? Do they mean multiply just y together? Just y by 5? Okay, it's a little bit ambiguous. So this is why this program was wrong, because I read the requirement too fast, and I wrote it the way I thought I understood the requirement, but I didn't really apply the correct syntax. So now I'm going to make an hypothesis on how to fix it. Now that I understand that the assignment statement is at fault. Now that I understand why it produced the result it produced, 55. Now I'm getting an idea about what went wrong. So it was really about that multiplication. So now I'm going to write this. Okay, I'm going to change my formula, and I'm going to make sure that both of them get multiplied by 5. And then I'm going to test again. And in this case, success. Okay. So generally you have multiple tests. You don't have just one. And it's just an easy example. But you would make sure that you pass all of the tests for that part of the code that you're trying to implement. And then once you have success, you can move on to the next thing you want to implement. But until you get success, do not try to add more code. Your code is broken. Okay. Imagine that you start building a car engine. You put two pieces together. They don't rotate right. You don't stop there. You don't fix that problem. You keep building an entire engine around those two pieces. Then you build the body of the car. You paint it. You do everything you have to do. Then you turn the ignition key. Why would it work? Now you just made it difficult for yourself to tear apart all this construct, to figure out where are those two pieces that were not spinning together, rotating with one another, that you remember having problem with. And once you spend hours building all this and hours tearing it apart and getting back to those two pieces, you find yourself where you were a few days ago, which is two pieces not rotating right. Same thing with programming. You write 5 lines, like for example here we have 4 statements. You write 4 statements. They do not work. They do not pass the test. Some of you are going to say, I'm bored. I'm going to write more code. I need to finish this assignment. And it's going to be a catastrophe. Heed my advice. Do not go to the next feature. Do not add code until your tests are passing. And this is probably somewhere in those advice here. Let's see. First, understand what happened and why. Understand things. Don't guess. Understand. Then you make an informed hypothesis on how to fix it. Informed, not random. Never succumb to the temptation of random programming. I write some code, I test it, the test tells me fail. I modify it randomly. I don't know what's going on. I just modify it. It fails again. Modify it again. Oh, it's passing. Must be working, right? No, that's not programming. I already mentioned that last week. It's like kicking and shaking an engine for a car until it's starting. That doesn't make you a mechanic. So if you do this, not only you're not going to develop programming skill, but sometimes, because the programs are so small in an introductory class, sometimes it might work, and that's actually the worst thing that can happen to your programming skill, because that's going to give you some sort of confidence that you were capable to get one program to work by doing it completely randomly, and then you're going to head to the exam And like I said, this is going to be a catastrophe, so let's avoid that, okay? If you find yourself doing this, drop me an email. Let's meet together online, one-on-one. Let's try to work on this, okay? Get you out of that bad habit. It's not uncommon for beginners. Don't get me wrong. A lot of people that just learn to program do this. That's why I'm pointing out, don't do that. It's so common. But really, if you find yourself doing this, talk to me. Let's try to give you better habits, okay? All right. Last programming skill, refactoring. We're not going to talk a lot about refactoring as we use Raptor. We could do a little bit of it, but really we're going to do more of it when we do Java. So I'm just going to give you the idea, the general idea. Refactoring is something you do when you have a program that does implement correctly a part of the requirement, a small part of the requirement, and it does it well, it passes a test, there's nothing left to debug. When you have something that works, then you take a break, you come back to your program, and you look at what you wrote, and you ask yourself, can I write it out? So, can I write it better? That's the general theme of refactoring. Better means different things. In this class, that means, do I need to add commands? Do I need to change the name of the variable so that it reflects better what they are meant to contain? Did I write a piece of code that is, a tangled mess of statements, but I could achieve the same result just with 2 statements? We are not trying to be crazy about optimizing in this class. We don't even optimize in program design, really. But we try to write code that's easy. We try to find the simplest, the easiest solution to understand to a computing problem. Okay? Producing a piece of code that works, but that is very complicated, makes you look very smart, because everybody looks at your code and say, I don't understand what he or she is trying to do. But in the end, this is actually a very bad thing. Code that is difficult for others to understand means that if there is a mistake in it, they probably will not see it. They will probably even stop looking at your code because you write code that's so obfuscated that they don't want to spend 3 hours trying to understand what what you are trying to do. So in a programming team, this ends up actually creating a mass of code in a project that nobody wants to touch, nobody wants to understand. And the truth is that in 6 months, you go back to that code that you wrote, and you're not going to find that you're that smart. You're going to find that you're really confusing. So we try to always, it's natural the first time you solve a program, it's natural to have a complicated solution. But we try to always go back to it once it works and try to rewrite it. So we don't add features. Our rewrite doesn't add features to our program. Our rewrite lets the program do exactly the same thing, but we try to improve the quality of the code. We try to simplify it, okay? And this is where tests are very useful. Because what you want to do is, when you have your code that works, so you run it through the test tells you, okay, this code works. Now you're going to modify a part of the code. You're going to improve a part of the code. You want to run it through the same test, because if those tests start failing, then you didn't refactor. You broke something. You changed the behavior of the program. You wanted to just improve how the program does its job, but not what job the program does, and you ended up, changing something. So if that's the case, undo your refactoring, undo your improvement, okay, and try again to improve and refactor, but be careful to not change the behavior of the code. So do it and use the same test again and again and again and again until the test pass. And then, when they pass, it tells you that you successfully improved your code without changing its behavior. So you see now how tests are so useful for programmers. Because if we did not have tests, every time you try to improve your code before to turn it in on an assignment, you would take a chance to break it. It was working, but now suddenly it doesn't work. But if you have a list of tests, okay, you have a list of tests, you have a test table somewhere, and you know that with this input and that output you expect that, you can very easily go through all the tests every time you modify something. It takes you 2 minutes, 3 minutes, 5 minutes maybe, but you are sure that you are not breaking anything. The quality of your test helps you guarantee the quality of your refactoring. So all the pieces are starting to fit together, right? So concretely, there are very different ways to do things to do like to write one program that satisfies a set of requirements, there are generally very different ways to go about it. So each student comes up with a slightly different solution. Okay, this is based on the fact that programming language allows you to write the same thing in different ways. Kind of like a natural language like English allows you to describe an object different ways. You still describe the same object, but there are different perspectives on it. Well, kind of like the same thing for programming. Let me take a practical example here with our simple Raptor program. This equation here, this formula, this expression here on the left that we wrote to fix the bug in our program is not really great. There's redundancy in it. We use 5, the constant 5, 2 times. Redundancy is one of the enemies of a good program, because one day you're going to modify that 5, you're going to say it's x, times 5 plus y times 6, and you're going to update that value, but you're going to forget to update that value. Redundancy in a program is always a source of mistake. You forget, that you have to keep those two things in sync. So instead, what we do, we use parentheses. Parentheses to say evaluate this first, then multiply the results by 5. Okay, so x plus y, for example, this is 3 plus 5. Okay, so that would give us 8 times 5. There we go, times 5. That gives us 40. Okay, the parentheses are used to identify parts in an arithmetic expression that need to be evaluated together first, before the multiplication in this case. Okay, so that's what we did here. And this change, before we commit it, before we say this is my program, it's better, we need to make sure it passes our test. So let's try again. 5 and 10 were the values that we used for our test. We expected 55. We got 55 with the left version. We still get 75 with the right version, and I think I said 55, sorry. Let me re-say that correctly. With 5 and 10 for x and y, we expected 75, and we got 75 with the left version of the program. And then we still got 75, so we still pass our test with my refactored version that is less redundant, that is easier to read too. Okay? So this is what refactoring is about. So to be able to do refactoring, again, you need to know your language constructs. Okay, what is this in Raptor? What does it do? What does this one do? What does the assignment do, right? Okay, you don't know that, you cannot do tracing, you cannot do implementing, you cannot do refactoring. Refactoring put a spin on the differences and similarities between the assignments, the different statements. Okay, can you replace one by the other? So in the example I've used so far, it really doesn't make that much sense, because except reformulating, the expressions, the mathematical expression, there was really nothing in our program we could reformulate. It's that simple of a program. When we start dealing with conditional statements, iterative statements, there's going to be much more we can do there. So stay tuned. Refactoring is going to really bloom during Module 102, 103. Never start refactoring before you have something that works. It's like trying to polish, your car project, car mechanic project, before you even have the body assembled or something like that. No. Get it to work. Always something I'm going to repeat over and over in this class. Get it to work, then improve it. Get it to work, prove that it works, then improve it. And something that works, the definition of works that we're going to use in this class is that you pass enough tests to give you confidence that your program is implementing all of the requirement accurately. Okay, so all the requirement accurately, yes. Most of you probably, make sense of that. Enough tests gives me confidence. Why are you being so vague? Well, I'm being so vague because testing is more an art than a science, and actually it's very difficult to prove in a mathematical sense that a program does what it's meant to do. It's actually a very open-ended research problem in computer science. Okay, so what we try to do with testing often, and it works, let's say 90% of the case, just to throw a number there. 90% of the time we are capable to develop enough tests, not too many, but enough tests to gain a very high confidence that our program is working. It's not perfect, it's like statistics, there's a margin of error, okay? But for 90% of the bugs that you would encounter, this is enough. and then there is the dreaded 10%. Well, the good news is that in this class, you are most likely to encounter this kind of situation than the dreaded 10% or whatever the real percentage is. And so this approach, this definition of a program works, and this approach to testing will be sufficient. If you are really interested in software testing, I really recommend that you took an elective in the BSIT that's called, what's it called? Software Maintenance and Testing, I think, or Programs Maintenance and Testing, Application Maintenance and Testing. It's taught by Carol Hockey, generally, and I really recommend you take a look at it if you are into programming and interested in testing more particularly. Last programming skill, designing. And this is the one we are going to talk maybe the least about in this class, because we are going to always deal with easy design problem. When you take IT program design, which is the next programming class after this one, then we are going to do the opposite. We are going to talk a lot about design approach, and we're going to try to solve difficult programming problems. But right now, for the introduction to programming, you got a good idea already that you know, we have like 5 skills to cover. That's a lot in one class, okay? And these are skills that are necessary. Tracing is necessary, implementing is necessary, debugging is necessary, testing out the other skills, and refactoring is probably the skills that is the least necessary. We could have you produce bad quality programs that work, and that would be good for an intro to programming. But while we are at it, we're going to try to also teach you, how to write good code. That's such a groundbreaking idea. Well, let's try to teach you to do things right? But designing is really combining all those skills together pretty much, and taking requirements that have absolutely no detail on how the program will do the job, just what it needs to do, okay? And that is not the same as implementing. I'm going to illustrate it into the next slide. Actually, let me jump to the next slide and show you. Here's an implementation question at an exam. Here's a design question at an exam. The left one here, the implementation question, tells you everything your program needs to do step by step. I could have written this, as I did in the previous slide, as an itemized list, of almost pseudo instruction. I chose to give it a form that is an English paragraph, but it is ultra detailed. It is a description of a solution. Okay? This is what an implementation question is. A description, a detailed description of the solution that you translate into Raptor, or that you translate into Java, or whatever programming language you're asked to use. A design question is a problem. It's a description of a problem and of what your program needs to do. It's a description of a behavior without any concern about how you are going to implement it. How many variables do you need? When do you assign a value to the variable? When do you compare to variable? When do you This doesn't belong in a design question. This is why design questions are harder, because implementation is really about translating a solution. Designing a program from scratch, just based on requirement, is about finding the solution, then implementing it, then testing it, and so on, so forth. Okay? So I want to make sure you understand, because some people think that implementing is pretty much coding, and coding is pretty much programming. No, programming is about problem solving. So in this class, the kind of problems that we solve are going to be relatively rudimentary. In program design, the type of problem we solve are going to be a little bit harder. And in this class, we are going to spend a lot of time talking about the 5 basic skills, okay? Tracing, implementing, testing, and refactoring. In IT program design, we are going to still talk about those skills, because we learn a new language, so we need to develop those skills on the new language. But most of the time, we spend in design, okay? How to design programs, as the name of the course suggests. So going back to the previous slide, this is what you're going to do when you program. In this class, a little bit, and much more even when you take IT program design. You are going to pick what I call a micro feature from the requirement. In program design, we have requirements that are like 1 or 2 pages long. So we could not possibly dream of implementing all of that in one shot. In this class, you have requirements that are much smaller. Okay, when you start playing with JavaBat, when you start playing with problems, you're going to see that the problems are really bite-sized. So you are not going to feel the need to necessarily break down those requirements in smaller pieces, but try to do so regardless, because it's how you're going to learn to program very well. Take a small objective, some small thing that you can implement now that's easy, and that's going to get you closer to the final result your program is supposed to achieve, right? We call that a micro feature, a sub-part of the requirement. Then design code to implement, to satisfy that subset of requirement, implement that code, test it, debug it, and when it debugs, when it's completely debugged and it works, pass all the tests, refactor it, and keep doing that until you're done. So, advice on designing tech IT program design. Well, you don't have a choice anyway. It's one of the core course of the IT curriculum, BSIT curriculum at USF. But it supplements this course. It's really fun stuff. It's getting you to the point where you are really solving problems much more bigger, much bigger than the ones we solve in this class, okay? I try to ramp up the difficulty progressively, so we are going to have small programs to design in this class. Then program design, we have longer ones. Then by the time you take IT data structures, which is also a core course of our curriculum, then you're going to be able to tackle much bigger, more complex programs. So there is a progression. That's why we use several courses to teach programming, because we cannot possibly teach you the fundamentals and problem solving and handling large problem in one semester. That would be completely catastrophic. Okay, so let's summarize everything that we have discussed, and I'm almost done with this slideshow. What you see here is an example of requirement that we use in the first module of IT program design. So by the end of this course, you will be able to implement this kind of stuff. Okay. I used a very unreadable font because when we start program design, I use an introduction that is similar to what I presented to you today. Obviously, it's not based on Raptor. It goes more in depth about designing, a little less about the other skills, but the idea is to expose the programming thought process as well. Why? Because a lot of people take programming concept with other instructors, and by the time they take program design, they have never heard of a programming thought process, so I need to brief them up. And one of the first assignments that I use is pretty much something that you would find in a final for programming concept for this class. The way that I write it here is really unreadable because I'm trying to convey the idea to my student that requirements are always unreadable. It's kind of like a end-user license agreement. You know, when you get those 10 pages of text that are written with a font that is fixed size or whatever, all caps, unreadable, that just really doesn't make you want to read or makes it easy for you to read this, okay? So this is how I look at requirements. Requirements are a big block of information that at first sight is unreadable. And you are going to have to learn to break it down, isolate, little pieces that you can implement, and then put them together. So based on your requirement, this is what I mean by extract features. By extract features, I mean you are going to take this requirement and you are going to say, for example, well, okay, they want me to write a program which read a positive integer from the user, and I'm going to just implement that first micro feature. So then you design your hypothesis. How am I going to implement this? How is my program going to do this? Then you implement your hypothesis, your program. Then you test it. Then once it passes the test, you refactor, and there you go. Okay. Another thing that's going to happen is as you read the requirement and as you decide that you're going to read positive integer, you are going to not only design an hypothesis on how to do that with a program, but you're going to also start writing down tests in your test table that say, well, this is what my program is expected to do. Reading a positive integer means that if I enter 42, it should be okay. If I enter 0, well, depending on how ambiguous the requirements are, maybe it's okay. Maybe 0 is not included. But if I enter -1, that should be the smallest integer, negative integer that should be refused by the program. So here we go. I have already 3 tests there just by reading, 2 words in the requirements. So that's the overall process. And as I already mentioned when we talked about debugging, Sometimes your tests do not work. When your tests do not work, then you need to trace your code to identify what part is responsible for the difference, then understand why there is this difference in the observed behavior of your program, and then you design a new hypothesis, you implement it, and you test again. And you keep doing this until you pass your test, at which point you can go ahead and refactor. This diagram is the entire programming thought process. This is the entirety of this diagram is what we are going to talk about and work on this semester with IT programming concept, and next semester or whenever you take it with IT program design. This is actually our focus for those two entire class. And we revisit the same concepts until not only you get the idea of the C language, the Java language, and Raptor, but you also get the idea of this process, and you get the idea of how things are implemented inside programming languages. Okay, so that you have a great theory, a great model of what's happening in a computer when you execute specific statement. That's our goal for those two courses, pretty much in a nutshell. So programming is an iterating process. Making errors is part of the process. Let me go over those concluding slides. Okay, programming is an iterative process. There we go. Let's go back 2 slides. You start extracting one feature, one part of the requirement. You go through this loop. You realize that there is a bug. It takes you 3 iterations in this loop to fix the bug. Then you refactor, you implement. You implemented one part of the requirement. That was number 1. Then let's go for number 2. Okay? Implement, test. Oh, this one works immediately. Okay, great. Number 3. Implement, test. Okay, need to fix, refactor. Number 3 is done. You see how we keep following the same path over and again. This is a process I advise you to follow when you learn to program. As you get better at programming, you're going to take shortcuts. You're going to go through that process much faster. But right now, I prefer you to go slow and do the right thing so you develop the right skills, rather than, you know, like try to go very fast to do whatever with your hands, and then, oh my God, it worked, but I have no idea how I got it. Well, this is going to give you very weak foundations. So go slow. Follow my advice. This process has been designed to teach. I told you that part of my research is about programming education. This process has been designed over the last 12, 13 years to address most of the problem that novice programmers, people who just learn to program, encounter the first time they learn to program. So there's been a lot of work, a lot of research and thought put into that process. I'm not claiming it's going to be great for everyone. You know, everybody has difference in the way they learn and they like to learn. But I'm saying that based on the problem I've seen my students and other students nationwide struggle through, as reported in the computing education research literature, this addresses those problems. So for some of you, it's overkill. For some of you, it's going to be really exactly what you needed. And for some of you, maybe you don't see how to leverage it, you don't see how it fits, or maybe it doesn't really fit for you. If that's the case, this is where I invite you to email me and be honest about it. Tell me, you know, this is not helping me learn to program, so I can meet with you, so I can try to understand exactly what's blocking you, what's hindering you, and then try to reformulate my explanation during office hours, one-on-one, so that I help you make usage of whatever in this diagram is useful to you. Okay? But the default is, yes, use that diagram. I didn't lecture on this, you know, for you to say, ah, whatever, I'll do it my way. There is a reason for which I present this diagram. Please try to apply it, okay? All right, so the big idea is that it's an iterative process, which, as a corollary, as we mentioned last week, means that you are not going to get it right the first time, okay? The only thing that matters is that every time you make a mistake, you have a process to examine these mistakes, revisit it, understand why it was wrong, and then fix it. As long as you understand each of your mistakes, a mistake is not a setback. It's an opportunity to learn. If you start making mistakes, you don't understand what was wrong, but somehow you're lucky or you modify things randomly and you get the program to work, that's not going to carry you very long. Okay, you might be able maybe to pass barely this class. Program design, you're going to have tremendous issues, and then IT data structure, that's going to be the end of it, pretty much. You're going to hit a hard limit. Okay, so making mistakes is part of the programming thought process. Don't feel bad about making mistakes. This is actually how you're going to learn to program. So that means many hours spent making many mistakes, and that's actually how you become a better programmer. All right. So I already told you many times, I'm going to skip over this fast. Decide what small feature you will implement next, what small solution you are going to use to implement it, then implement it. Emphasis is on small, okay? Do not write more than, I don't know, 3-5 statements at a time before to test. It's not a magic number, it's a rule of thumb. So sometimes you're going to write 10 and you're okay. Sometimes one statement is going to force you to test already. But make sure that you go very incrementally. Small step at a time, okay? There's nothing worse than a student writing an entire flowchart in 5 minutes and then spending the next 3 hours trying to figure out what this flowchart is doing, okay? That's the wrong way to go about it. Sometimes it's best to do tabula rasa, to just erase everything and start again from scratch. Sometimes you dig yourself into a mess with a piece of code that you wrote too fast. That's not worth spending hours trying to fix. You have to restart and do it incrementally. Now, I told you that I was going to explain to you how to program. I told you I was going to give you a process, you know, the PTP, Programming Thought Process. This is a great name. There is a little bit of a lie in there, and I know that most of you already caught onto that. Some of the steps of the Programming Thought Process are almost mechanical, meaning that I can give you very accurate guidelines about what to do, how to do it. And then some steps, like design an hypothesis here on what your solution should be like, and design an hypothesis on how you should fix that bug. These are not these are not mechanical steps. Okay, this is where I cannot give you an algorithm. You are going to have to understand the base material from the study material. You are going to have to see how it's used in the apprenticeship video. You are going to connect the dot with the model I gave you, the programming thought process, and then you are going to actually use your own intelligence, creativity, and adaptivity to be able to do those steps. So this is not where algorithms shine. This is not where I can give you a mechanical process. This is not something that machines can yet automate, okay? So depending on your perspective, and I'm going to conclude with this, if you are a pragmatic guy or girl, you're going to look at this as job security. That means that a machine cannot do this. That means there's going to be still employment for IT professional programmers and stuff like that. If you are more into sci-fi, and there are many different examples we can use here, you can see that as a temporary state of affairs, okay? Maybe one day the machine will be able to program themselves and generate hypotheses on how to solve a problem, etc. And to be truthful, my other area of research is actually evolutionary computation, which can be seen as a branch of artificial intelligence. And yes, we do have actually technique to have machine, quote-unquote, program themselves using different models. So it's not as clear-cut that I make it sound, but it's definitely not yet, you know, the kind of stuff that you see on this slide here, the movie level, you know, artificial intelligence and stuff like that. We are not yet there, but it's a very interesting field. If you're ever interested about, you know, just understanding what AI is about and stuff like that, don't hesitate to ask me questions. I love to talk about that stuff too. I'd be glad to address your question. But now, I mean, the kind of question that I'm expecting are probably not about the movies that were illustrated on the last slide or AI in general, but question about this specific slideshow. So if you had any question first, I was hoping you would interrupt, okay? Don't never feel bad about interrupting. I expect that, I recommend that. I'm going to open the floor for a few seconds in case somebody wants to ask a question while we're recording. They want their question recorded in the session. And then if I don't see anybody typing, I'm going to, or taking the mic, I'm going to close this recording. And we are going to open the floor for Q&A, not recorded. Okay, so hang in there, I'm not leaving. We're going to have time to discuss one-on-one after the session. Okay. I don't see anybody typing, so I'm not trying to rush you, but I'm going to stop the recording, and I would like, again, to thank you, everybody who attended first. This was a long session, 2 hours. Like I said at the beginning, The next session would not be like this. Okay, the next session maybe I'll have something that I want to point out based on questions that were asked on the forum for 10 minutes or something like that, half an hour maximum. I'll try to keep it under half an hour. And then once I'm done passing that message and recording it, it's bring your own question. BYOQ type of session. Okay, come to me with practice exercise you're struggling with, question you have, and those sessions are going to be much more interactive, but I needed to lay the foundation, and I think that last week we took care of laying the foundation on how we're going to work, and this week on pretty much how we are going to learn programming. So we should be ready for next week to start pretty much treating those weekly live sessions as pretty much office hours. Okay, so come with your questions, and I'll be glad to help you live. So thank you everybody who was able to attend, who took the time to sit through a 2-hour-long session. Thank you everybody who is going to actually download the video or play it in Blackboard Collaborate, and who has the patience to watch a 2-hour-long video on programming. Let me know if you have any questions. Use the forums. I'll be glad to help you out. Keep in touch. Keep the dialogue going. And this is pretty much it for tonight. So thank you again everybody.